For pi 1 this is pi I, but we have no idea what I actually is. It will depend on the particular situation. Okay, so only thing we know is that we will be left with m minus n prime elements. Since m minus n is positive, so there exists some prime element say let me call it pi k prime, that appears in S. S is a product of such primes. So in S, there one of the primes is pi k prime. Because m minus n is positive, at least one prime will be here. But then from this equation, what do we get? But then pi k prime divides 1, because 1 is a multiple of pi k prime. This is a contradiction. Okay, why is it a contradiction? A prime element dividing 1, this creates a contradiction. In the case of integers, we already know, we are almost so familiar with the contradiction that we take it for granted that no prime number can divide 1. However, in this case, you have to figure out why this is wrong. That I leave to you. Okay. From here, you try to get a nonsensical result. This leads to something wrong. It cannot happen. This is a contradiction. So our supposition is wrong. That is, n cannot be less than m. We must have, so the other possibility is n is greater than or equal to m. Similarly, one can show that m should also be greater than or equal to n, because if one starts the process, all these arguments from the right hand side, not from the left hand side, and works with the primes pi 1 prime, pi 2 prime, etc., assuming that m is greater than or equal to n, then assuming that m is less than n, then one will ultimately, running all these arguments, one will conclude that m is greater than or equal to n. So n is equal to m. This proves that n is equal to m. Now, once you have the fact that the number of primes on both sides of the equation are equal, then you can run a similar argument to prove the remaining part of this theorem, which says that every prime on the left hand side is an associate of a prime on the right hand side, and the argument will be just like on this part. You see here, pi 1 prime is an associate of pi 1. So like that, we can continue the proof. Now, arguing like what we already have, already have above. With the equation we can prove that each pi I is an associate of some pi j prime, where j now also varies from 1 to n. Note the small change that we have made here in light of what we have proved, that n is equal to m. Now the number of terms on this side also, in place of m we can write n. And now we carry out the same procedure, considering first pi 1 and then concluding that pi 1 is an associate of pi I for some I on this side. Pi j for some j on the right hand side, and conversely every pi j prime is also an associate of some pi I from this side. This, and conversely each pi, say j, k, l, m, n. Okay, so all of them have been taken. Each pi p prime is an associate of some pi q. So this ends the proof. So we can now combine the fourth lemma, which is about the existence of factorization, prime factorization, and this theorem which says about this form of uniqueness of this factorization. We can conclude this. So combining, okay, I need to refill again, give me a moment. Combining lemma 374 and the above theorem, we conclude that every non-zero element in a Euclidean ring is either a unit or can be written as a product of finitely many prime elements and this product is unique up to associates. Unique up to associates means there is no essential difference between the primes that appear in two possible factorizations of the given element. The only thing is that they are associates, and this product is unique up to associates. So this is the full form of the unique factorization theorem, although the theorem that we have had just now, that is named as the unique factorization theorem. Okay. Now finally, after having all these things in a Euclidean ring, let us now consider ideals in it. We have already seen that all ideals are principal ideals, but if you remember, in the ring of integers, particular types of ideals are maximal ideals. There also all the ideals are principal, because that is also a Euclidean ring, but those ideals are maximal precisely, which are generated by prime numbers. So a similar result here is true. The ideals, the principal ideals that are generated by the prime elements in a Euclidean ring, they are maximal and conversely. So this is our final result from this section. So this is the seventh lemma. So it states this: the ideal A equal to A is generated by the element A naught, where A naught is not equal to 0, is a maximal ideal of the Euclidean ring R, if and only if A naught is a prime element in R. So the fact that every ideal is like this, every ideal is a principal ideal, we have already seen that in the very first result that we have seen in this section. So now among them, the maximal ideals are those that are generated by prime elements. So let us see the proof. Okay. So we will first show that if A naught is not a prime element, then this ideal is not a maximal ideal. Let us just first prove that. That if A naught is not a prime element, then okay, I have included this extra condition. I think this time Herstein is right. I don't need this. We will see. Then A is not a maximal ideal do I need this condition or not? What happens if I have a equal to 0? I think I will need this condition. We will see. Okay, let us first finish the proof, then we will see. So assume a naught is not a prime element. Okay, since it is given that a naught is non-zero, so either a naught is a unit or a naught has a non-trivial factorization. Since a naught is not equal to 0, either a naught is a unit or a naught has a non-trivial factorization in R. What happens if a naught is a unit? Then the ideal generated by a naught is the whole ring. Then A is equal to R, and hence A cannot be maximal. Because a maximal ideal by definition is a proper ideal. R is itself never a maximal ideal. And how is it that if a naught is a unit, then A is equal to R? You take the inverse of a naught, because a naught is a unit, its inverse exists, and multiply a naught with that inverse. By the definition that A is an ideal, that product will belong to A, which is nothing but the unit element 1. Now whenever 1 belongs to an ideal, that ideal has to be the whole ring. We have already seen it way before in the very beginning of ring theory. Okay, so A naught cannot be maximal. Now assume A naught has a non-trivial factorization in R, that is A naught is equal to BC, where neither B nor C is a unit. Also note that neither B nor C is equal to 0, because if one of them is 0, A naught will be 0, contradicting this given condition. Okay. Now consider the ideal B, which is being generated by the element B. Okay. Since B divides A naught, here we mention, note that B is not equal to 0. That's why divisibility by B makes sense. Since B divides A naught, that we are getting from here. So what will happen? all the multiples of A naught are automatically also multiples of B. Now all the multiples of A naught constitute the ideal A, so they are automatically multiples of this small b. So this capital A, this ideal is contained in this ideal B. We have A as a subset of B. Okay. Now our aim is to show that A is not a maximal ideal. So we have got an ideal B in between A and R. Had A been maximal, B would be equal to either A or R. So if we can show that if B is equal to neither A nor R, then automatically A cannot be maximal. So we will try to show that now by contradiction, of course. Suppose A is equal to B. This condition does not mean that A is not equal to B. It just says that A is a subset of B. A may very well be equal to B, and that's what we are supposing now. This will lead us to a contradiction, hopefully. So we have supposed this. So that means what now? So B belongs to B. Since B belongs to B, we have B belongs to A, and hence since B belongs to A and A is being generated by A naught, so this small b will be a multiple of A naught. B is equal to K A naught for some K belonging to R. We now use this here. Then A naught is equal to BC. This is equal to K A naught C, which implies one is equal to KC. Again, keep in mind that we are able to cancel A naught from both sides because A naught is non-zero. So A is equal to KC. But then C is a unit in R. Which is a contradiction, because according to our assumption, neither B nor C is a unit. So our supposition is wrong. That is, this cannot be true. That is, we must have A properly contained in B. Another contradiction we are hoping if we suppose that B is equal to R. So let's just proceed to that. Next we suppose B is equal to R. Since 1 belongs to R, because R is a Euclidean ring, it has a unit element. So that comes from the corollary to our first result. Since 1 belongs to R, we have 1 belongs to B, and hence 1 will be a multiple of small b. 1 is equal to LB for some L belonging to R. But this implies B is a unit in R, which is again a contradiction. Because neither B nor C is a unit. So our second supposition is also wrong. That is, we must have this is wrong. B is equal to R. So B should also be properly contained in R. We thus have A properly contained in B and B properly contained in R. This shows that A is not a maximal ideal. A cannot be a maximal ideal because we have found a proper ideal containing A. So, excuse me. So, what have we proved here? We have proved that if our element A0 is not a prime element, then the ideal it generates is not a maximal ideal. What is the contrapositive of this statement? Namely that if the ideal capital A generated by A0 is a maximal ideal, then A0 has to be a prime element. That's what we have proved. Let's just write that. Thus, if A0 is not a prime element, then A equal to A0 is not a maximal ideal. Or equivalently, if A equal to A0 is a maximal ideal, then A0 is a prime element. This is only one half of the proof. Now we have to prove its converse, namely if A0 is a prime element, then this is maximal. Don't get confused between the two parts of the proof. Although we had to prove this, but we proved its equivalent contrapositive statement because that is somewhat easier to prove. Now conversely, Conversely, we excuse me. Conversely, assume that A naught is a prime element. We have to now prove that capital A is a maximal ideal. So we consider an ideal containing capital A, then try to show that that ideal is either equal to capital A or the whole ring. Let U be an ideal in R such that A is contained in U and U is contained in R. We are going to make use of the fact that U is also a principal ideal. That means U is also generated by some element, because after all U is also an ideal in our Euclidean ring. Okay. Since R is Euclidean, U is equal to U naught for some element U naught in R. Actually U naught in U, sorry. Okay. Since U naught belongs to U, we have so now what we want to prove? We want to prove that either U is equal to A or U is equal to R. Okay. No, we don't start like this here. I mean, we don't continue like this. Now two cases will arise. Either U naught is a unit or it's not a unit. If U naught is a unit in R, then we have seen it a number of times that the ideal would be equal to R. So we assume U naught is not a unit. Okay. Okay, now using the fact that A naught divides U naught, we will try to conclude something, not a unit. Since A naught belongs to A, we have A naught belongs to U, and so A naught will be a multiple of U naught. A naught is equal to what do I take? Say, let me take D U naught. Okay, things are getting jumbled, no? Cluttered, with this space is cluttered because we don't have our perpendicular bisector. So A naught is equal to D U naught for some D belonging to R. Okay, so now it's quite easy. you see a naught is assumed to be a prime element, and we have written a naught as a product of two elements in the ring. So from the definition of prime elements, one of these two things has to be a unit. But now according to our assumption, u1 is not a u0 is not a unit. So that means we must have d as a unit, since a naught is a prime element and u naught is not a unit, d must be a unit. Okay, but then if d is a unit, then we can write u naught is equal to d inverse a naught. So what do we conclude from this? From this we conclude that a naught divides u naught, that is